Okay, in the last PowerPoint, we talked about numbers and measurements and how to do them. One of the things I talked about briefly is zeros, and we want to go more in depth in how to look at zeros, because sometimes zeros really kind of can get messy because of how we look at them. Not just in science, but in math and other places. And a lot of times when you see a zero, zero sometimes this means nothing, okay? And sometimes zeros just is there, okay? It's just put there, and sometimes it really has meaning. And so let's talk about how to deal with zeros. Okay. Okay, so zeros are a bit confusing just because they can be an actual value in a measurement, and sometimes they're just placeholders, and we want to go over that, and we have to be careful which is which. So let's say I have a scale that measures the hundreds. So I have this scale that measures 100, 200, and 300, and the divisions are hundreds, okay? And so I have this measurement right here. Okay, from the last video, we learned when we have a graduated measurement like this, you have the number that you can actually measure, the 200, and then you're allowed one more digit. So you allowed the hundredths and the tenths. Okay, so the number that I would write down, so this is about halfway. So I'm going to write down 2, 5, okay, 0. Okay, now this 0 here shows up nowhere on this scale, okay? All right, and so that's 0. It's almost like, why do you put it there if it's not? Because there's no once here, okay? So why do we put that 0 there? Well, we put that 0 because if we just wrote down 2, 5, which we're really allowed, so we're allowed to put 2 and a 5, we know that this is not 25. This is 200 and 300. So what we do is we put that 0 to represent that this is not 25, but this is 250. In this case, this 0 is a placeholder. Okay, even though it's not measurable, we put it there to tell us it's 250, not 25. Because you're only allowed to write 2 and 5. Because you have a 2, and then you have one more digit, 5. But you have to add that 0, okay, to tell us. Okay, well, 0 still doesn't count as a precision digit in this case. So I have to let you know, if I wrote down 250, and I didn't tell you where I got that scale, okay? All right, you wouldn't know if this 0, if I wrote 250, we'll talk about this in a little bit. I mean, this could be a real 0. I mean, it could be an actual 0 measurements where we allow the ones in account. So what you have to do is you have to tell the reader that this is a placeholder. And one way to do that is to put a line under it or over the 0. And that tells the reader that it's a placeholder and it's not part of the precision. The precision is 2 and 5. So the number of significant digits here are 1, 2, okay, not 3. Okay, so here's one way of writing it, 250 with a line under the 0. Another way that we'd actually prefer is to write as scientific notation 2.5 times 10 to the 0, because that wraps that 0 up into here. This tells me the magnitude. Okay, it gets rid of the 0, and so now I don't have to be confused by it. And this here tells me that the precision is 2. Okay, we'll go over scientific notation in a future slide. PowerPoint. Now let's look at a couple other measurements that are similar to the above in terms of the numbers. So let's say I have 1, 2, 3, 4 scales. and I'm measuring the same thing, whatever it is, okay? And so I have a scale from 0 to 1,000. I have a scale from one that measures hundreds, and then one that measures tens, and then one measures the ones. So, so all the scales should measure around 200, okay, because they're all measuring the same thing. But each scale has a different precision. So let's take a look. Scale A. All right, we're really only allowed to have, it's the thousandths. Okay, so really we only have a guess digit, okay? So our number that we really count is a 0, okay? So and then the next digit, which is the hundredths, is a guess digit. Okay, and we're allowed to write that, and so I'm going to write, so it can be 2, okay? And the other 2 zeros, all right, are placeholders. Or you could write it as 2 times 10 to the second. It only has one sig fig, and that sig fig is really just a guess digit from the scale. Okay, scale B, the numbers that are precise, the number that we're sure of, are the hundreds, and the guess digits are the tens. Okay, so here's my number, okay, and now I'm going to say it's 2, and I'm going to say my guess digit is 0, okay. So now I have 2 numbers, okay, 2 sig figs. I have 2, and that's 0. It counts. 0 counts because it's a guess digit. So now I have 2, 0, and then I have to put the other 0 there as a placeholder. So now it's 2, 0, 0 placeholder. So now we have 2 zeros. One's real measurable number, and the other one's a placeholder. And so you write this 2.0 times 10 to the second, and it has 2 figures. All right, so let's say you have this guy. Now you have a one where it measures to the tenths, you're sure of, and then the ones are the guess digit. So now you have 200. You're sure of the 200. You're also sure of the tens, 0. Okay, so you're sure of 2, 0, and then you're allowed one guess digit, okay, because you're sure of the tens, so you're allowed to go to the ones, and so now you're allowed to put the other 0. That's if it falls right on that point right there. So now you have 2.00 times 10 to the second, and it's 3 sig figs. Okay, scale D now goes to the ones, and then you're allowed to go to the tenths, okay? So it's 2, 0, 0. We're sure of all 3 of those digits, and then we're allowed to have one digit, which is a 0, okay? So now this is 200.0, or in terms of scientific notation, 2.000 times 10 to the second. Okay. So just by looking at a number without a scale, so let's say I wrote down 200. Okay. Okay, which one of these scales could it be? All right. It could be A, B, or C, the way I wrote it down here. Okay, because all of these have a value of 200. This has 200, this has 200, and this has 200. Okay, this one has 2.0, so that's different because it doesn't have 0.0 here. So if I write this down, you really can't tell if it's A, B, or C. All right, or it could be D, but really it's between these 3. So so if I just wrote down 200 without knowing the scale, you wouldn't know which one it is. Okay. So what you need to do is you need to ask the person that give you this number, okay, what scale did you use? Okay, did you use one that's between the thousands, the hundreds, or the tens? Okay, and then you can determine the number of sig figs. Now, if you've been taught sig figs before, the way they would say this, if you're just given this number here, what you have to assume is that it comes from the weakest scale, and so it comes from this scale. Because you can't give this more, I mean, if you're not sure about it, you can't give it more digits than you're sure of. And so you're really sure of only one, okay? Unless they tell you the scale you have, okay? So if I write down 200, okay, then it would only have one sig fig or a score of 1. Same thing goes with if I wrote down 20, okay? Unless they tell you what kind of scale it comes from, you would say it only has one digit, okay, a score of 1. Now sometimes I will be using, I'll write down 20, and I'll say this 0 counts, okay? So that means it has a scale that measures to the ones that we're allowed. A guess digit is allowed to the ones. Okay, so just pay attention with that as I go along. Okay, other numbering issues. Okay, so sometimes when we write down a number, you have to determine its score. So if I wrote down 31, okay, you would say it has a score of 2. Okay, but all right, there's sometimes like if you actually have a number of things like cows, I said, if you have 9 cows and I write down 9, it's going to be exactly 9. Okay, you can't have, there's no imprecision about this number. There are 9 cows. You can't have 9.5 cows. Okay, I mean, you could if there was an average, but we're talking about actually not counting the cows. All right. So if you had 80 cows and you actually could measure the 80 cows, then this would be a number that's exactly 80. Anytime you have countings, okay, that you're actually counting something, all right, then you're sure of the counts. It goes 1, 2, 3, 4. Okay, when you have counts, they will have infinite precision. Okay, so you actually don't count them. So if I said 4 cows times 3.1, okay. Now, if you didn't know this was cows, you would say this has a score of 1, this has a score of 2, and your answer would just have a score of 1. Okay, but if I told you it's 4 cows, I know this is exactly 4, then you would not include it as part of the sig figs, and your answer would have 2 sig figs. Okay. So we don't run into that often, but pay attention to it. So numbers are not just numbers. You have to pay attention to where they come from. Like in the last one, if we wrote down 40, okay, how many sig figs does it have? You can't tell really. Because first of all, you don't know if this is counting numbers. It doesn't, maybe 40 cows. From a scale, well, you could have, it could be have a this could be the only sig fig, and this actually be a sig fig. So you have to always know where your numbers come from. Given numbers, like we're going to be talking a little bit the ideal gas law, where we use the universal gas constant, and atomic masses. You write those will be given certain numbers, like I don't know, like the atomic mass for carbon, I think is 12.060 or something like that. this tells you it has 5 numbers, and you would count them all. Okay. Right, scientific notation. I don't want to spend a lot of time on this because hopefully you know how to do this. The basic thing about scientific notation is you always have, there'll be only one digit left of the decimal point, and then you'll have to the power of 10. Okay, so if you have 341 and you want to change that scientific notation, only the 3 will be left of the decimal point, and then the 0.41 would be to the right, to the power of 2. Now, I know there's all kinds of ways you count. You go count to the right, count to the left. You know, I just think about it. I go, well, 341 is 100, so that's power of 2, okay? So 3.41 times 10 to the second. If you have trouble with scientific notation, there's plenty of YouTube videos to show you how to do them. And I'm going to be giving you worksheets that have to do with scientific notation and sig figs after this video. As far as doing math with scientific notation, you have to be careful. You can multiply and divide when you have scientific notation. In fact, it's good to be when you do this. So let's say I have two numbers here: 2.2 times 10 to the third times 7.6 times 10 to the sixth. Okay. So the way that I like to do these, if I don't have, I actually like doing these without calculators because you can come up with a pretty fast number. I mean, I can tell you right off the bat, 2 times 8 is about 16. 10 to the third times 10 to the sixth is 10 to the ninth. So my answer is going to be 16 times 16 times 10 to the ninth, or 1.6 times 10 to the 10th. And you'll see how that's close here. Okay, so you can come up with rough estimates by doing this. And one way to do that is to do the number part separate from the exponents. So I do 2.2 times 7.6, and that's 16.72. And then you do the powers of 10. And then what you want to do is get in scientific notation. So the 1 point, so you're going to change this to scientific notation first. So it's 1.6 times 10 to the 1.672 times 10 to the first times 10 to the ninth, and so you get 1.672 times 10 to the 10th. And the number of sig figs we're allowed is only 2. This has 2 and this has 2, so my answer is going to be 1.7 times 10 to the 10th. Okay. So this part you have is not scientific notation. So the way that I do it is I've changed this to scientific notation and then multiply that by the extra exponent, 10 to the ninth. But, okay, you can't add or subtract when you're in scientific notation. You can't take 2.2 times 10 to the third plus 7.6 times 10 to the sixth and come up, you can't go 2.2 plus 7.6 and come up with your answer. What you have to do is change both of these to their number form. So I turn it 2,200 and then 7.7,600,000. Add those two together, and then change it back into scientific notation. This only has 2 digits. This is only 10 miles, so my answer can have only 2 digits. And when you do this, you turn out is that your answer is the same as this answer right here, as they're starting. And that the reason why that is because this number is so small, it's 1,000 times smaller than this, that it doesn't affect this value at all in terms of its precision. Okay, sometimes when you have scientific notation, it's useful to unwrap it and make it so you can understand it. So let's say I have three measurable values of the same, so I have 1.2 times 10 to the minus third, 7.6 times 10 to the minus third, 1.4 times 10 to the second. And what I want to do is graph these, okay? So if you graph this, 1.2, if you just graph the numbers, 1.2, 7.6, and 1.4, they go 1.2, 7.6, and down to 1.4. Okay, and obviously that's not what's happening. Okay, these numbers increase, so you're going to get a line that goes up. And so what you have to do is change this number here to the power of thirds. So that will make this now 14 times 10 to the minus third. Okay, and then what you got a graph, here's your 1.2, here's your 7.6, and here's your 1.4. Okay, so you'll see this when we do labs. Okay, the the recorder will give you these numbers here, and what you want to do is graph them. And so what you want to do is change them to values that can graph. And okay, so that does it for that part, and we're going to go on to the next PowerPoint, which talks about, well, we'll see. Okay.